Okay, so let's talk about section 14.1, basic definitions of Galois theory. By the way, if you have any questions at any time, just interrupt me and ask the question. So we have a ground field f, and then a polynomial with coefficients in f, and then we have the splitting field L. Right? So Galois theory is about the group of permutations of the roots of this polynomial and how they relate to the algebraic structure of the splitting field L. Right? Hold on. Oh, okay. So yeah, you have a polynomial with coefficients in f. You have its splitting field, and what we're concerned with is the group of permutations of the roots of f. So these roots belong in the splitting field, and permutations means you're sending some root of f to another root of f. And it turns out that these induce automorphisms on L. And so we'll be studying automorphisms of this splitting field. And the fundamental theorem of Galois theory relates this to the algebraic structure of the splitting field. By algebraic structure, I mean the subsets of L, or even the subfield lattice of L, like the lattice of subfields of L. So it turns out, like, knowing stuff about this group, which we're going to call the Galois group, gives us information about the subfield structure of L. It turns out, like, there's a what is it, bijective uh, inclusion reversing uh, correspondence between the subgroups of this group of permutations, or uh, group of automorphisms, and so subgroups of that, and subfields of L. And the correspondence is given by taking fixed fields of the automorphism groups, and by taking uh, automorphism groups the of L fixing that subfield. Anyway, I'll just quickly like go over all the stuff that was covered on Monday. So I'll just redefine everything because I have these notes. So an isomorphism sigma of K is called an automorphism of K. The collection of automorphisms of K is denoted auc K. An automorphism sigma is set to fix an element if sigma alpha equals alpha. The prime subfield of K always fixes any automorphism. Right? Why does this work? Well, any automorphism has to send 1 to 1. And once you know how it acts on 1, you know how it acts on the prime subfield, because the prime subfield is the smallest field obtained by doing field operations on 1, and an automorphism has to, preserve those field operations. So if the prime subfield is everything you get by doing field operations on 1, and the automorphism fixes all of those things, then the automorphism has to fix the prime subfield. Why is it called the prime subfield? So I don't know. That's like it's so like every field has a subfield generated by 1, and that's the prime subfield. Like, I don't know, why should it be called prime? I mean, it's just notation, right? Or terminology, but I guess prime meaning like it's always there, right? Kind of feels like a rational subfield because a prime subfield of R is Q, right? Yes. But you can also have like finite fields, and the prime subfield of a finite field is uh, the field having uh, prime p elements, right? So like a finite field. Let me just do a tangent here, right? So an example of a finite field, right? You're right. So like the prime subfield of R is Q, but the prime subfield of a field with like p to the k elements is fp. Because a field with p to the k elements has characteristic p, so 1, 2, 3, 4, dot, 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 p minus 1 and 0. This is the prime subfield, and that's fp. I guess it makes sense to call it a prime subfield because, like, if you have a finite field, or if you have a field of characteristic p, where p is a prime, then the prime subfield has p elements, and p is a prime. So, but yeah, if your field has characteristic 0, the prime subfield is q, right? Means the prime subfield is q. If your characteristic p, then the prime subfield is a field with p elements, where p is a prime. Okay. So yeah, examples of these things, examples of automorphism groups. Automorphism of Q. Well, Q is a prime subfield, is its own prime subfield. So the only automorphism is the one that fixes Q, which is a trivial automorphism. Likewise, automorphism group of FP is the trivial group one. Yeah. What about non-trivial automorphisms? Consider the field Q adjoint I. Its prime subfield is Q because this is a field characteristic 0, so prime subfield is Q. Also, like, you can easily see Q embedded inside of this field. Any automorphism of sigma, any automorphism sigma of this field has to fix the prime subfield Q. So it has to fix the rationals. So are there any non-trivial automorphisms in this group, the automorphism group of Q adjoint I? Any automorphism sigma is determined where it sends I, right? Because Q adjoint I, like, as an algebra over, I think, Q, like, there are two generators. Like, you're just adjoining I, right? So this is the only element that you're adjoining. And so the elements in Q adjoint I are like expressions of the form A plus BI, where A and B are rational numbers. And so if you tell me where I gets sent to, then you know where A plus BI gets sent to. Because A is rational, B is rational, they're fixed. I gets sent to something that you specify, and it's a field automorphism, so it preserves addition, preserves multiplication, and so on. So we just need to say where I goes to, but notice that we have this relation I squared equals -1. So since it's a field automorphism, it preserves multiplication. So sigma of I squared, wherever you send I, has to square to -1 as well, right? So that means you have to send I to another square root of -1. So you have to send I to plus or minus I. So the only non-trivial automorphism is the one that sends I to minus I. And you're familiar with this as complex conjugation. All right. Let K over F be an extension of fields. Write K over F to denote the collection of automorphisms. K fixing F. Examples: automorphism Ri over R is the trivial automorphism and complex conjugation. K is equal to K over F, where F is a prime subfield. We already said that any automorphism of K fixes the prime subfield, so the automorphism of K that fix the prime subfields are just the automorphisms of K, right? And now is the part about, like, the fact that aught K over F is a group. So if you have two automorphisms of K, their composite is also an automorphism. You just compose automorphisms, you get an automorphism. So aught K is a group and aught K over F is a subgroup. Any automorphism of K has an inverse because they're automorphisms, they have to be invertible. So it's a group. And furthermore, this is a subgroup because if you're an automorphism that fixes F, right? Say you have two automorphisms that fix F, then their composition also fixes F, right? Yes. And the inverse of an automorphism fixing F also fixes F. So they're both in the subset, so it's a subgroup. Okay. If you have a question, just ask the question. So proposition, if you have a field extension and an algebraic element in the extension, then any automorphism of this extension has to send that algebraic element to another root of the minimal polynomial. And this, so in other words, the automorphism group permutes the roots of irreducible polynomials. Oof, okay. Yeah. Any polynomial with coefficients in f having alpha as root also has sigma of alpha as root. The proof is like any automorphism on a polynomial of x is that polynomial on sigma of x. This is because automorphisms preserve addition and multiplication. So what is a polynomial anyway? It's like just addition and multiplication that you do to x and field elements in f, but sigma fixes f, so it fixes the coefficients of f. Yeah, so you can see this. And then, so if alpha is a root of p of x, then sigma of 0 equals p of sigma of alpha. So sigma of alpha is also a 0 of p, right? Okay. If K is generated over F by a collection of elements, then sigma is completely determined by what it does to, what it does to the generators. So why is this? Yeah, so like if it's generated by a set of elements, then sigma is determined by what it does to the generators. Because what does it mean to generate this field over this field? You're just taking polynomial combinations of those generators with coefficients in the smaller field. And so what does sigma do to a polynomial? It just, yeah. So if you know what it does to the generators, then you know what it does to a polynomial combination of the generators as well. All right, another note, if you have a finite extension, then you can conclude that the automorphism group is finite. So why? So K is finitely generated over F by algebraic elements. All right, so you have a finite dimensional vector space over F, so you have finitely many algebraic generators of K over F. And then using proposition 2, the number of automorphisms of K fixing F is finite. Why? So if you have any generator alpha, then any automorphism has to send alpha to sigma alpha, which is another root of the minimal polynomial of alpha. But there are finitely many roots, so there are finitely many options you can send this generator to. But you have finitely many generators, so you have finitely many automorphisms. So this is a finite group, right? So if you have a finite extension, you have a finite automorphism group. And then the fixed field is a subgroup. Okay, so here we're changing perspectives a little bit. We're looking at a field. We're looking at a subgroup of the automorphism group and saying that the fixed field is a subfield. Yeah, you can prove this just by using the definition of subfield. And then an important remark is like this correspondence is inclusion reversing. So if you have a field F1 is contained in F2, which are subfields of K, and then look at the automorphisms groups fixing these subfields. So the automorphism group of K fixing F, and the automorphism group of K fixing F2, right? So you have F1 is included in F2, then the automorphism group of F2 is included in F1. So it's inclusion reversing when you go in that direction. The reason for this is like you're looking at automorphisms of K that fix F. Wait, hold on. Yes, yeah. You're looking at automorphisms of K that fix F. And if you have an automorphism of K that fixes F2, then that's automatically an automorphism of K that fixes F1. So if you have something in here, it's automatically in here. Because if you fix F2, then you're also fixing F1 because F2 contains F1. So that's this forward direction. And then if you have if you have subgroups H1 containing H2, then the fixed fields are included in each other, but in the reverse direction. And yeah, why should this be the case? Like if you have something that's fixed by everything in, if you have an element in this field, it's going to be fixed by everything in here. Since this is a subgroup of that, it's going to be fixed by everything in here. So it's also in here. So everything in here is in here. If that didn't make sense, like just try thinking about it. And yeah, it can be confusing, but yeah, if you think about it, it'll make sense. Okay, so that's basically a review of stuff that we've seen before. Are there any questions before I move on to the new stuff in section 14.1? Okay, let's see. This kind of inclusion reversing reminds me of the algebraic geometry context. I'm not sure, ideals, varieties kind of thing. Yeah, so yeah, I can see that, yeah. Yeah, it's kind of similar. Okay. So now the first question of the remaining part is, how many automorphisms are there of a splitting field? So why am I thinking about splitting fields first? Because we know that if you have an algebraic element alpha in an extension, then any automorphism has to send alpha to another root of the same polynomial, the minimal polynomial of alpha. So it takes alpha to its conjugates, and there are finitely many options. The splitting field gives you every single option, right? So if you have alpha, then you have all of the conjugates of alpha as well, because it's a splitting field. What does conjugate mean in this context? Conjugate means alpha, the conjugates of alpha. So you have the minimal polynomial of alpha, right? Alpha is an element of the extension. Minimal polynomial has coefficients in F, right? And any other root of the roots of this guy are the conjugates. Okay, and so the situation we're concerned with here is a splitting field, meaning you have a polynomial p of x, then you have a root alpha. No, I need. So you have a polynomial p of x with coefficients in f, and then the splitting field of this guy is up here, right? It's an extension of f. And so if you have a root of alpha, so a root of p of x alpha, then any automorphisms of the splitting field has to send alpha to another root of the same polynomial p of x, because automorphisms preserve field operations. Okay. So why are we thinking about splitting fields? Because a splitting field contains all of the roots of p of x. So we have the maximal number of automorphisms, if you will, right? We have the maximum number of options to send alpha to. So this is this is the case where we have the biggest automorphism group. Anyway, let's just focus on splitting fields. So proposition 5, let E be the splitting field over f of the polynomial f of x with coefficients in f. Then the number of automorphisms of E fixing f is at most the degree of the extension E over f. And it's equal when f of f, the polynomial, is separable over f, which is most of the time. Like separable is a condition that's like if you're not separable, then like you're in a bad situation. Either like but most of the time, like any irreducible polynomial over Q is separable. So most of the polynomials we know, right? So if you have in the general case, the automorphism group of a splitting field will equal the degree of the extension. Okay, so let's prove this. So just remember what we're trying to prove. We're trying to prove that the automorphism group has order less than or equal to the degree of the extension. And in the generic case, when f of x is separable, which is usually the case, it's an equality. So the automorphism group has order the degree of the extension. So why is this the case? What does it actually mean for f to be separable? Okay, so f is separable if the roots of f are all distinct, right? So if you go to a splitting field K, I keep forgetting. If you f of x has all of its roots in K, right? So I don't know, alpha 1, alpha 2, ... alpha n. Let's say this is a degree n polynomial, and it has n roots in K. Well, if it's separable, then it has n distinct roots. That's what separable means. And any irreducible polynomial over the rational numbers is separable. So it's like usually you don't even think about separability. It's I don't know. Okay, so the proof. Okay, so recall theorem 13.27 from the previous chapter about extending automorphisms. Hold on. Okay. So this theorem is about extending automorphisms to splitting fields. So if you have an isomorphism between two fields, and then you have a splitting field, E of f, then you can extend the isomorphism to an isomorphism of the splitting fields. So how are we going to prove the statement? We're going to use this result and appeal to induction. So the number of extensions sigma. So sigma are the extensions of these isomorphisms F. Okay, I should say the situation we're concerned with is when F equals F prime. So you have an automorphism of F. And then the splitting field E equals the splitting field E prime. So you have an automorphism E. So you're given the identity F, and then you're given, yeah, the identity F, because you want sigma to extend the identity. You want sigma to fix F. We're concerned with automorphisms of E, which fix F. So you're looking at how many extensions of the identity do you have, right? How many automorphisms of E do you have that fix F? And to answer this question, we're actually going to consider a more general case where you have an isomorphism between two fields. So they're basically the same field, but you have an isomorphism, and then you're going to look at extensions of this particular isomorphism to the splitting fields. How many of these extensions do you have? The number of such extensions specializes to count the number of these automorphisms that fix F, and that number will always be less than or equal to the degree of E over F. And when E is a splitting field and F is separable, that number is equal to the degree of E over F. So the key assumptions here is that E is a splitting field, and F is separable, but that's usually the case. The real assumption is that E is a splitting field. Okay, so we're going to do induction on the degree of this extension, right? So the base case is when the degree is equal to 1. In this case, the splitting field is equal to the ground field. So there is a unique extension, sigma equals phi. Yeah, there's one, the degree is 1, and the number of extensions is 1. The number of automorphisms is 1, so it checks out. Now the induction step, all right, I have to fill this in. So we're really going to do induction. So we're going to assume that the degree is greater than 1. So is greater than 1. All right, so E is a splitting field of a polynomial, right? So f of x in this guy. And let's say an irreducible factor of f of x is p of x. P of x is an irreducible factor. It's an irreducible factor of the polynomial which we're taking the splitting field of. And so let's say it's also it's an irreducible factor with degree greater than 1. Why does there exist such an irreducible factor? Because if all of them were degree 1, then f of x would split in f, right? So the extension would not be greater than 1 degree, because all of the roots of f would already be in f. So there has to be some irreducible factor with degree greater than 1, and let's call that one p of x. And p of x corresponds to p prime of x, which is an irreducible factor of f prime of x in this field, this polynomial ring. Okay. Now let alpha be a root of p of x. Um, all right, so alpha is the root of p of x, and let, what is it? Tau, wait, all right, so let sigma be some extension. So we have this picture. Let me draw the picture. So the picture is you have sigma extending tau extending phi. And this is, phi is an isomorphism from F to, from F to F prime. And sigma is an isomorphism from E, the splitting field of the polynomial F, to E prime. And in between, we have the intermediate extension F adjoin alpha. And this is isomorphic to, so what does, so sigma restricts to tau on F of alpha. And what is sigma of alpha? It's some root of, right? Sigma of alpha is a root of the corresponding polynomial p of x with coefficients in f prime, right? So let's say this is beta, and this is the root of p prime of x. So we get the extension, so this gets mapped to f prime of beta. So this is a subfield of that, this is a subfield of that. Yeah. Okay, just to make this clear, what's happening, you're starting with this, phi is an isomorphism from f to f prime, and then you're picking some extension sigma from e to e prime. The existence of this guy is given by theorem 13.27. And then you're restricting sigma to the subfield generated by alpha. And since sigma is an isomorphism, it sends this to an isomorphic subfield of E, and it sends alpha to a root of P prime of X. So you're adjoining a root of P prime of X. Yeah. And if this field was generated by F and alpha, then this field is generated by F and sigma of alpha, which is beta. Okay, so that's the situation. Whenever you have an extension of phi, then you have this kind of diagram. Okay, and then conversely, for any beta of root of p prime of x, there exists extensions tau and sigma giving such a diagram. So we just need to count the number of diagrams that look like this. Okay, so how many extensions tau are there? Well, it's going to be the number of distinct roots beta, because so at this point we're using the induction hypothesis, right? We're okay. Sorry. So we're using the induction hypothesis to count the number of automorphisms tau. And this number is equal to the number of roots beta. And this is the degree of p prime of x. Well, it's at most the degree. It's equal in the case that you have a separable extension. And then this is the degree of the extension f prime of beta over f, which is the degree of f of alpha over f. I think one note just crashed. Okay, so does it make sense that if you have any automorphism, no, I mean any, if you start with an extension sigma, let's say you have an extension sigma, that you can get such a diagram. That makes sense, right? Yes. And now if you start with beta being a root of p prime of x, then you can get a tau and a sigma. Why should it be the case that if you pick a root of, yes, So alpha has to be sent to some root of p prime of x, and if you give me p prime of x, then yeah, you can find an isomorphism tau, and then right. So sigma determines beta, and beta gives you some sigma, which then gives you back the same beta, right? So right, so picking a sigma determines beta, and picking a beta okay. So any sigma gives such a diagram, and we need only to count the possible number of these diagrams. Okay, so for any beta, so alpha is always fixed, but for any beta, you can find some sigma and tau that give you this diagram, right? And for any sigma, you can get this diagram as well. So yeah, beta does not uniquely determine sigma. Beta does not uniquely determine sigma. No. But beta does uniquely determine tau. Right. Yeah. Okay. I think I'm gonna stop for today, and all right, I'll go over this part much better for next time on Friday.